Faraday's law feels like this confusing thing when you're learning it, especially based on equations, based on anything like that. It just feels off. To me, it feels a little bit like learning to play a new card game, and then you realize all you really needed was to play a couple of open hands, and now you understand. So let's play a couple of open hands of Faraday's law. So I'm going to have a region with a magnetic field. And I want to stick a couple of loops in here. Loop 1 will move this way. Loop 2 can move this way. We'll stick a loop 3 over here, and a loop 4 that moves this way. In each of these cases, I'm interested in finding the direction of the induced current, and I'm going to approach it this way. I am always going to answer these questions. I want to know what my magnetic field is right now. I want to know how it's changing, what my magnetic flux is right now. I want to know how that's changing. I'm going to find the induced magnetic field, and then from that I want to find my induced current. I also know that these two will always be opposites, so once I've got one, I'll have both. Because that's my framework every time, I am just going to copy paste it for each loop. So loop 1, loop 2, loop 3, and loop 4. Let's get started on these. What I would like you to do after the first loop, probably, is to pause before we go through each loop and see if you can go through the whole process first, and then we can go through this together. This way you can use that as a self-check. Loop 1. Right now I have a certain amount of magnetic flux because part of my loop right here is exposed to the magnetic field. So the flux that I have points into the screen. That flux is changing because my loop is moving downward. A moment later, like just a split second later, my magnetic flux will be greater because more of my loop will be exposed to the field. As soon as I have my change in flux, I know my induced field has to be the opposite. So I have this induced field in my loop that points out of the screen, and in order to get that, I'm going to right hand rule this thing and find that I need a counterclockwise current. That's loop 1. On to loop 2. Loop 2 right now has this part of its loop exposed to the magnetic field, so I have a flux that points into the screen. My change in flux, a moment later I will have less flux, so I am subtracting from what I've got. To subtract is the same as adding the opposite, like adding the negative, right? So it must be in the opposite direction of what I've got, and as soon as I've got my change in flux, I know my induced flux has to be the opposite, my induced field. So I have in this loop, this induced field that points into the screen. To produce that, I need a clockwise current, and I can say, I know that to come out of the screen I needed counterclockwise, so now I have to have clockwise, or I can right hand rule this thing. And I've got that. Loop 3. Loop 3, I have this much of my loop exposed to the magnetic field. So I have a flux right now that points into the screen. a moment later, I will have the exact same amount of loop exposed to my field. So I have no actual change in flux. Now, down the line, as this loop keeps moving down this way, yes, eventually this thing will lose some, but I'm not worried about what happens down the line. What I want is right now and a split millisecond later. So right now I'm here, a moment later there's not going to be any change. If there's no change, then there's no induced field. If there's no induced field, there's no induced current. That's loop 3. Loop 4, flux right now points into the screen. The change in flux, right now this points into the screen because of this region. The change in flux, well, a moment later I will have less of my loop in the field, so I am losing flux. Once I've got that, I know my B induced has to be the opposite, and in order to get a B induced that points into the screen, I need an induced current by right-hand rule that goes clockwise. That is Faraday's law in action.